In this video, we're going to talk about AutoML, specifically AutoML application in the public health and disease prediction scenario. Our title here is AutoML, Everyone's Venture of Machine Learning, which pretty much describes AutoML's most important feature, its ease to use and very low entry threshold. So in this challenge, we are given a problem which asks us to predict brain cancer survival outcome. We were given an original data set of 3 components. The first one is a gene expression data set. It's a log2 normalized gene expression profiles of over 19,000 genes and on 377 samples. We were given a clinical phenotype dataset of 4 different categories. The first phenotype is sex, and the second one is race, and third one is cancer type, which includes four cancer types, and the last one is a WHO grading of cancer stages, which consists of 3 levels of cancer grading. And the last part of the dataset is cancer outcome, which is 1 that represents death outcome and 0 which represents survival. The reason why we are using AutoML for this dataset is because of the strong capabilities of AutoML. Traditionally, machine learning models were produced over a very long time horizon, and it takes a professional team to produce a single model because we need specialized personnel for data collection, feature engineering, model selection, and data optimization, and last but not least, model evaluation and final deployment. But with AutoML, we have a very fast implementation of machine learning because the program of AutoML itself helps solve the problems of feature engineering, modeling, optimization. Those processes no longer need human intervention. So for AutoML, human experts only need to do data pre-processing and the last step, which is deployment. For this project, we use the following tools or libraries to perform the challenge. The first one is AutoSKLearn, which is our main AutoML library. The second one is Pandas, which is used mostly for data pre-processing. And we also use a little bit of TensorFlow, which is used to make random forest fillings. Before we implement our AutoML process, we need to do a little bit of data engineering to prepare our data sets for AutoML inputs. So in data engineering, we first did pre-processing on the genetic expression data. We did it in 3 different ways. The first method is PCA dimensionality reduction. And the final result was that PC1 expresses most of the genetic variances, over 90%, which is actually 92% of the genetic variance was explained by PC1 alone. And the second method was differential gene analysis. We used 10 genes in this case. And the last method, we used the original expression dataset, and we just did a simple log2 normalize for that dataset. And in terms of phenotype data pre-processing, what we did is mostly just filling the missing data in the dataset. The first method we used was a simple drop NA, which is we drop all the samples with missing phenotypes. The second method was filling the missing phenotypes with randomly generated phenotypes. The third method was just marking the phenotypes as the missing phenotypes as unknown. The last method, which we discussed earlier, was to use a random forest model to fill up the missing data set based on the information of the expression data. Overall, we have 3 different expression data preprocessing methods and 4 different phenotype data preprocessing methods. And combining those two, we end up with 12 different data sets containing different combinations of preprocessing methods. Afterwards, we did our AutoScaler model building. For each data set, we applied AutoML classifier with default hyperparameters, and we set the maximum running time length of AutoML to 2 hours. After each data set generated a model, we did a 5-fold cross-validation of the model. And the final result was that the best performance model was generated from the data set that replaced missing data with randomly generated content, and for the genetic expression data, the best option was to use differential gene analysis. The model we used to predict the outcome, because DEG analysis is not available for prediction dataset, we replace and the best and we replace and we use the replace NA with the replace missing data with randomly generated content, that version of model, and the log2 normalized data, and use that version of the training data sets to come up with a model for the ultimate prediction task. And overall, the best model has a precision of 0.9455, an accuracy of 0.9497, and the max F1 score was 0.9419, and the AUC was 0.91. And throughout the challenge, we faced a couple issues. The first one is the bias in the data set. We realized that the data set is quite biased as it has a significant biases in its mostly in its phenotype section. Firstly, it has an ethnicity bias, meaning that most of the most of the patients' data in the data set is ethnically white. Over 90% of over 80% of the samples are classified as white people. But in reality, we don't have that many white people in the world. So this comprises as a ethnicity bias. And secondly, we have a gender bias, meaning that the female and male samples are not well balanced. And lastly, we have a cancer type bias, meaning that some cancer types are underrepresented. Also, we face another issue, which was the missing fields in the phenotype dataset. This is covered by using different filling methods, as we discussed earlier. And here is a brief analysis of the AutoML tool and library we used. We used AutoScaler, and we decided to use this tool for a couple of reasons. Firstly, it has a algorithm advantage over other open source AutoML libraries, namely MLBox and AutoKeras. AutoScaler has over 100 built-in algorithms, while MLBox only has over 15 algorithms, and AutoKeras even less, about 10 algorithms. And the second reason that we choose AutoML of AutoScaler is that it has the best hyperparameter tuning methods among the open source AutoML tools. For AutoScaler, it uses Bayesian optimization method, which has proved to be more efficient than traditional grid search and random search tuning methods. While MLBox and AutoKeras both use a combination of grid search and random search, which is less efficient and more costly than AutoScaler, meaning that they are more resource intensive in terms of their training process. And lastly, AutoScaler is very easy to use. There's a very simple API and a very clear display of the most important information for ML beginners. And the AutoML models tested in our challenge are those built in by AutoScaler, mostly random forest, gradient boosting, and support vector machines. Now we have concluded our challenge. Here are a couple thoughts we had on the application of AutoML for the FDA. So when implementing AutoML, it must be done with extra caution, especially for a government agency like the FDA, because FDA holds a lot of sensitive data. If not treated properly in an AutoML process, which is a black box process, this might in some ways lead to data leakage and data breach, which can cause severe trouble for the agency. And for the same reason, we recommend that the FDA monitor its process for AutoML. Make sure that all the data exits are well guarded, minimizing any risk of potential leakage. And lastly, although AutoML is very easy to use and it generates decent results, we must not limit ourselves to this method. We should keep up with the new developments in the fields of machine learning models and cross-compare AutoML results with other machine learning techniques, making sure that we're always on the right track of machine learning. And despite all that, we should still understand the vast amount of opportunities that AutoML is opening up in the FDA. Firstly, AutoML can greatly increase efficiency. It can automate repetitive tasks and free up FDA staff to focus on higher level tasks that require human expertise and judgment, instead of focusing on those trivial tasks as model optimization and model evaluation. And secondly, AutoML has a very high accuracy for its ultimate model. Therefore, it can reduce errors and improve accuracy of FDA's decision-making processes, such as during drug approval and medical device clearance processes. And thirdly, AutoML can greatly increase the productivity of the agency. It can help the agency to process large amount of data quickly and efficiently, enabling faster review and approval of new treatments and therapies. AutoML is able to organize large amount of unstructured data, such as therapy records and medical journals, which is traditionally hard to collect and archive. And lastly, AutoML allows for better decision making. It provides the agency with data-driven insights and recommendations, enabling more informed decision making on the broader scale. Lastly, for AutoML, very limited experience is required as an operator. It only requires the operator to have some knowledge of data cleansing, some basic level of Python coding, and some basic knowledge of ML model evaluation. With just those knowledge, a personnel is easily able to master the process of AutoML. Pretty much everyone can do it. and thank you for tuning in for this presentation.